In B1, we are given set of a subset of functions from uh, different vector spaces, and we're asked to show if it forms a subspace. So here, when showing whether or not it forms a subspace, we've got two conditions. We've got non-empty, and for all C in F slash X, Y in uh, W, Cx plus y is in W. Now, this Cx plus y, if it's functions, we typically use f and g. If it's matrices, we typically use a and b. If it's vectors, we use x and y. But we're looking basically non-empty and closedness. So here, the first thing we're going to do is we're going to look at non-empty, and we could show it has any vector, but having the zero vector is typically the approach. And the reason why it's typical is if we don't have the zero vector, it's not a subspace automatically. So either way, we get an answer. So here, if I look at my functions, my zero function is z of x equals 0 for all x. So consider z of x, which equals 0 for all x. Note z of 2 equals 0. Thus, z is in W. And if you look at this, the z function's in W. Remember, W is a set of functions. So here, z is in W. Now, the next thing I want to look at is I'm going to let C be in F and FG be in W. Then F of 2 equals 0 and G of 2 equals 0. I'm going to consider C plus or CF plus G. Let's write that a little nicer. CF plus G. I want to show it's in W or want to show it's not in W. So I'm going to consider what CF plus G of 2 equals. Well, this equals CF of 2 plus G of 2 by definition of function addition, which equals CF of 2 plus G of 2 by definition of function scaling. And this equals C times 0, because f of 2 is 0, plus G times plus 0 as F and G are in W. So this equals 0 plus 0, which equals 0. Now, CF plus G of 2 is 0, thus CF plus G is in W. Therefore, by the characterization of subspaces, by closure theorem, W is a subspace. In this set here, I'm given the set of functions, the set of real valued functions such that f of 2 equals 1. Now here, if I look at z, consider z of x equaling 0. Note z of 2 equals 0, which does not equal 1. Thus, Z is not in W. As the zero vector is not in W, W is not a vector space. Therefore, W is not a subspace. In B2, we determine if this matrix is in the span of these vectors by completing the following step. First, we construct a system of equations such that the solution will help you answer this question. Provide a short explanation for why this system of equations will help you answer this question. Well, 1, 2, 1, 4 is in the span of the set of matrices 3, 4, minus 1, 4, 2, 3, 0, 3. It's in the set of those matrices. If and only if there exists an A, B in F such that A 3, 4 minus 1, 4 plus B 2, 3, 0, 3 equals 1, 2, 1, 4. If and only if there exists an A, B in F such that, now I'm going to look at this right side and consolidate, expand. So 3A plus 2B, 4A plus 3B, minus A and 4A plus 3B equals 1, 2, 1, 4. If and only if there exists an A, B in F such that 3A plus 2B equals 1, 4A plus 3B equals 2, minus A equals 1, and 4A plus 3B equals 4. Finally, this is true if and only if AB is a solution to the system of equations. So there's two scalars, AB, such that this holds. That means that the vector AB, the F tuple vector AB, is a solution to the system of equations 3A plus 2B equals 1, 4A plus 3B equals 2, minus A equals 1, and 4A plus 3B equals 4. So by answering this question, does a solution exist? So there exists an AB that is a solution to this system. So does a solution exist? So now we construct an augmented matrix that represents our system equations we constructed in the previous part. So the augmented matrix would be 3, 2, 1, 4, 3, 2, minus 1, 0, 1, 4, 3, 2. That is the augmented matrix that represents our system equations. Now solve for the echelon form of the matrix you created in B, provide appropriate justification. Here, this is solve for the either row echelon form or row or reduced row echelon form. And we're, instead of using, so we're going to compute the row reduced or the reduced row echelon form, or RREF. And we're going to, in this example, use Gauss-Jordan elimination. So what I'm going to do is, when doing these row operations, I can pick my pivot row, and I'm going to pick it so that my life is a little bit easier. I just noticed a mistake from the previous one. There should be a 4 at the bottom. I'm going to pick this to be my pivot. That's going to be my choice of pivot. So I'm going to take R2 swap or R3 swap with R1 to make it -1, 0, 1, 4, 3, 2, 3, 2, 1, 4, 3, 4. Then I'm going to do 1 over -1, R3, R1 replacing R1 to give me 1, 0, -1, 4, 3, 2, 3, 2, 1, 4, 3, 4. R2 -4, R -4, or R1 replaces R2. R3 -3, R1 replaces R3. R4 -4, R1 replaces R4. 1, 0, -1, 0, 3, 6, 0, 2, 4, 0, 3, 8. Now what I'm going to do is I'm going to take row 1/3, row 2, replace row 2 to give me 1, 0, -1, 0, 1, 2, 0, 2, 4, 0, 3, 8. Now row 2 -2, row 1 replacing, or sorry, row 3 -2, row 2 replacing row 3, and row 4 -3, row 2 replacing row 4. This gives me 1, 0, -1, 0, 1, 2, 0, 0, 0, 0, 0, 2. R3 swapping with R4 gives 1, 0, -1, 0, 1, 2, 0, 0, 2, 0, 0, 0. And now we're going to continue, even though at this point you could answer the question. So we're going to do R3, 1/2, R3 replacing R3 to give us 1, 0, -1, 0, 1, 2, 0, 0, 1, 0, 0, 0. R1 plus R3 replacing R1, and R2 -2, R1 replacing 2R3 replacing R2 gives the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. And this is our echelon form. So given that echelon form of the matrix, we're asking, does there exist an AB such that AB is a solution to the system A equals 0, B equals 0, C 0 equals 1. And this is inconsistent. Therefore, no solution exists. Thus, the matrix 1, 2, minus 1, 4 is not in the span of our set of matrices, which we can see here as 3, 4, minus 1, 4, 2, 3, 0, 3.